Hello, in today's video we're going to talk about how to get unlimited power by plugging in a power extender into itself. Anyways, in physics, power has a very different and direct meaning, and by the end of this video you'll have a decent understanding of power and work through a problem that involves implementing this idea. Power is the time rate at which work is done. For example, if you had lifted a 200 Newton weight, for example. We'll draw our little weight here. 200 newtons. And you lift it at 1 meter. So you're going to lift it up this distance. You'll have a work of distance times a force, which equals 200 newtons times 1 meter, which gives us 200 joules of work. But the problem comes to looking at this unit right here is how long is that work being done for? We can describe this term in terms of power, and to introduce more power, or what is known as watts, it came from James Watt when he discovered that a horse can pull around 33,000 foot-pounds of work per minute, and that kind of tells you that power has nothing to do with electricity, and we just use it as a way to measure energy and power. And so one of the ways we can find power for power, the average of power, for example, we donate it as P average, or power average, equals the change of work over the change of time. And that's how we're going to find it. Notice that power is a scalar quantity in this example right here, just like work and time. So these are all scalar quantities. They don't have direction. And we can also find instantaneous power, and we donate it by writing P as power equals the limit of time as it goes to 0 right here, times the change of power over the change, the change of work over the change of time, which equals dW d work, which is this basically means like a small segment of work divided by time gives you your power. And we donate those as watts, as I mentioned it before. So we get watts. This is how you spell it. And we donate it as a large W, which is, yes, that's exactly how we donate work. So it may or may not get confusing. You just have to look at the problem. Hopefully there's some context to it. Like if it said like kilowatts, you can't, because this is a standard unit, you won't see kiloworks. Work is like power, so like P equals whatever 10 watts, and then work equals 10 joules. And if it's in this format, you can always tell which W goes where. And there's some different units we can convert watts into. So for example, 100 watts equals 1 kilowatt. So that comes from the metric system where there's a thousand. Never mind, not 100. And we can also convert 746 watts into 1 horsepower from James Watt from before. That's where you defined horsepower. Now that we introduced power and its units, we will go over some problems to see how these apply. So we'll go to the next page. Let's say we have like a marathon runner that's running up some stairs. So let's draw some stairs here. And she's running up here. The marathon runner weighs 500 kilograms in this example, and she's actually running up the stairs to the tallest building in America, which is Chicago's Willis Tower. And this building is around, let's say this is the top of the building up here, is around 443 meters. And to lift herself from all the way from the bottom to the top takes her around 15 minutes, which is pretty fast. I think so. It sounds pretty fast for the tallest building in America. Now we need to express this. We need to find how much power she was able to output, like an average power, and then convert this into kilowatts and then horsepower. So let's first convert this 15 minutes into seconds so we can use our units we would use as typically. So we have a mass, and then we have our, so work or power equals the change of work, so this is average power, equals the change of work over the change of time. So we have the time, we don't have the work, but we can most likely find it. So we find that the work equals the force that's being applied and the displacement. We have the displacement. We know what the work, we don't know the work at the moment, but we can find it in a second using our free body diagrams. We know that whatever force she's like pushing up is equal to the force that's pulling her down, since that's the force she needs to pull up to get up. So it's going to be mg, and this is the Newton force that's been pushing her up. So we know that it equals to mg. So work equals mg displacement, and then that gives us a work. So let's solve for work. So work equals 50 kilograms right here times g, which is 9.8 meters second squared, or per second, second squared doesn't make too much sense, but so we have 443 meters, and we'll calculate this out to be 2.17 times 10 to the fifth power of joules, because we can see right here meters squared, second squared times kilograms is our units for joules. So now that we have work and we have our time, we can now find the power. So power equals, or average power equals 2.17 times 10 to the power of 5 joules divided by 900 seconds, which in the unit wise will give us kilograms over meters squared. So watts equal, and then over seconds cubed. Here's so to the power of 3. And that's going to be our units. And now let's calculate how many watts we're going to get, which should be around 241 watts. 0.2. Now let's convert this into kilowatts. So remembered we divided this by 1,000, which gave us 0.241 kilowatts. And to convert this into horsepower, we divide the watts by 748 from what I can recall. Divided by 748, which will give us 0.322 horsepower. And that's all for today. Now now we have an idea how to use work, and if this video helped you, don't forget to like and that lets me know that this is actually helping someone out.